For 2.1 notes over power and radical functions, we are really going to keep things basic. We are going to keep things small here, but I just want to point out this chart. Lots of test and quiz questions right off the bat, right up here. What I would like to point out to you is there are basically two types of monomial functions. Remember that the word monomial just means one term. So you're just going to have one coefficient stuck to the letter x and then maybe an exponent. And the exponent is what is going to determine the nature of the graph. The coefficient is going to determine the end behavior. So remember, the coefficient, I'm just going to abbreviate, determines the end behavior, and your exponent determines the shape. Now, since it's one term and it's going to have an x next to it, look, all of these examples go through the origin. So that's very important that you remember all monomial functions go through the origin. And before we get too far ahead, there's something else that I would like for you to remember now, and there is something called positive and negative functions. So I'll just write this at the top. We're going to have something called positive functions, and positive functions are going to have a positive coefficient. Positive functions are always up on the right. And what I mean by that is I am talking about it is up on the right side of the coordinate grid, like this. Notice you have an arrow up over here on this upper right section of the coordinate grid, quadrant 1. Quadrant 1. Then we're going to have something on the flip side, which are negative functions. And remember, negative functions are going to have a negative coefficient, the number in front, and it is always down on the right. And I am talking about the right side of the coordinate grid on the right side of the origin. So if you notice right here, we have a negative function. Notice this graph is going down on the right side of the origin. Okay, so let's go ahead and talk about some similarities and some differences. First of all of your even functions, whether they are positive or negative, are going to have all real numbers for the domain. Not the case for the range. So if you notice, the range is restricted either above 0 or below 0. Now, on your positive and odd functions over here, these are always going to have the same domain and range. So even functions are going to have a restricted range. Odd functions are not going to have a restricted range. Also, if you notice, we are having symmetry come back. It is always symmetrical around the x-axis for an even graph. It is always symmetrical around the origin for an odd graph. What makes something even and what makes something odd? Quite simple. What makes it even or odd is the exponent. So the coefficient is going to tell you whether it's positive or negative. The exponent is going to tell you whether it's even or if it's odd. Let's go ahead and take a look at this first example. So actually, let's analyze both of them at the same time before I continue. So what we have here are some power functions. I have a monomial raised to an even power. I have a monomial raised to an odd power. They're both considered positive functions. They're both considered positive because they have a positive coefficient. However, the shape, they're going to look completely different. Now, I am going to go ahead and work this out with you. I would not give you crazy values like this without access to a calculator. Now remember, we can have domain be any positive or negative number here. So I'm going to kind of just stick 0 right here. We're going to do -1 and we're going to do -2. We're also going to do +1 and +2. And these don't even matter because it's not even going to fit on this picture. So -2 to the 4th power is going to be a positive 16. And then when we take half of that 16, that's going to give us an 8. Now remember, a negative 1 raised to an even power is going to be positive 1. And then positive 1 times this coefficient is just a half. And of course, when you plug in 0, it turns into 0. Positive 1 to the 4th times a half. Positive 2 raised to an exponent of 4 times a half. Let's go ahead and plot these ordered pairs. So we're going to have negative 2, positive 8, negative 1, just kind of estimate where you think that half might be. Of course, it goes to the origin, and then we're going to graph the other points over here. And then it looks like a parabola, but remember, it is not a quadratic, it's a monomial raised to the power of 4. So truly, all of your even functions are going to look like a parabola. They're U-shaped in nature, as long as their exponent is even. Now let's take a look at an odd. Now remember, I can plug in any values. The domain is negative infinity to positive infinity. We're going to keep them pretty small. I could plug in negative 2, but you're going to see in a moment it's just not going to fit on the graph. We'll even do positive 2. So negative 2 to the 5th power, negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. Negative 8 times negative 8 times negative 2 is going to be a negative 16. And then negative 16 times one more negative 2 is going to be negative 32. But then you have to multiply that by 3. So that's going to give us negative 96, which of course is way off the graph. And we can go ahead and plug in a positive 96, which again is going to be way off the graph. These values we're going to be able to plot. Remember, negative 1 to the 5th power is just going to be a negative 1, so this is going to turn into a negative 3. Of course, that's 0. And then when we plug in a positive 1 right here, of course, that's just going to be a 3. So even though I can't fit these, remember, it's going to behave the same way as a cubic. If you notice, it looks like the parent cubic function, and this kind of behaves the same way. You're still going to have a little swirl behavior right there. And then let's go ahead and describe the domain, range, intercepts, and end behavior. And let's also review where it's increasing and decreasing. So for the domain, this is going to be negative to positive infinity. For the range, it's going to be 0 to infinity. The domain over here on this guy is going to be negative to positive infinity, same with the range. Go ahead and copy down the same thing. All right, intercepts. So easy because the x-intercept and the y-intercept are the exact same thing. We're just going to write the ordered pair for the origin on all of these for both of these graphs. 0, 0, 0, 0. Okay, where is the function increasing and decreasing? So if you notice, this function right here is decreasing. And guys, remember, when we talk about decreasing and increasing, no brackets. So this is going to be negative infinity to the 0. Then right here, it hooks around. There's no movement. It's considered standing still. That's why we use a parenthesis. Then it turns around and it increases from 0 to positive infinity. This is not the case. If you notice, if I kind of trace this graph or even trace it with my finger never goes to the bottom of the page. This graph is increasing from negative to positive infinity. There's no decrease on this graph. Now, just to wrap things up, notice that it goes on from negative infinity to positive infinity for domain. Very important, all power functions, whole number power functions with regular exponents will have domain from negative to positive infinity. And every monomial that you have, whether it be even or odd, is going to look and behave the same way. So this is a great general statement for power functions. This is a great wrap up for it. All right, let's go ahead and talk about radicals.